And Dan, I will turn it over to you.
Kelly, thank you very much. And thank all of you for joining us today on another session of Webinar Wednesday. My name is Dan Hani. I am the Director of High Performance HVAC Solutions and Corporate Educator for Veritech. My background is a little unique. I do not have an engineering degree. In fact, my degrees are in fine arts. I acquired my Bachelor of Fine Arts degree from University College London at the State School of Art, and my master's degree at Boston University in sculpture. I began in this industry in 1985 as an estimator working for Norman S. Wright Company. And after a few years, I moved into sales, contractor sales, and joined a company in 2000 called Air Specialty Products. I was actually their first outside salesman hired other than the owner himself, Ron Campton. I worked in the capacity of contractor sales until 2008 when I became Air Specialty Products sales engineer. At that time, I desired to really do something a little different, and I realized I could have an impact on a topic that I am certainly feel very strongly about, and that's the need to build a more sustainable environment for our children's future. And consequently, started on a program of self-education and engineering principles, especially with a focus on high-performance HVAC systems. In 2016, Veritech reached out to me and wanted me to focus purely on education and engineering sales. I took advantage of the excellent opportunity they've granted me. And most recently in 2022, they brought me to the position of Director of High Performance HVAC Solutions, where my goal is to educate our community on why high performance mechanical systems are certainly doable. They can be certainly affordable and offer a very impressive solution for reducing our carbon footprint on the environment. I've had the great privilege of co-authoring a number of articles for Engineered Systems magazine. I've co-authored 6 and written one of them myself. Over the years, they're all available through the archives at Engineered Systems magazine or ES magazine. The 2 most recent articles are on 100% outside air passive radiant cooling and heating systems. And in August of 2023, I did a feature article for ES Magazine on the Helios building here in Phoenix that applied an innovative approach to chill beams. We actually let the chill beams condense in that project. And I'm pleased to say, when I interviewed the facilities engineer for the article, there was only one thermal complaint in that building, which far exceeds ASHRAE Standards 55 requirements. So we'll leave it at there. Please realize that much of the material that I present on here will be available in various forms on these articles. So let's move into today's 100% outside air systems and the importance of ventilation. As all of my presentations are very dense with material, no apologies for that. The reason being is there's only so much you're going to remember as to what I say today during this lunch and learn. So we want these PowerPoint decks to be available resources in the future. So if you wanted to go back and review, reflect, or recall the information that I covered, and then some added ballast as well, will be available at our website under the training tab in the resource library group. So let's move on with today's presentation. The 100% outside air systems and the importance of ventilation. It's very important, I believe, that before we start talking about HVAC systems or needs in the market, that we give some sense of context to why it's relevant, why we are actually doing that. So I'm going to aspire to do that here for you here shortly. So we're going to look at the EPA, the CDC, and ASHRAE with regard to ventilation rate statements. We're then going to look at a conceptual overview of what a 100% outside air system is. And then we're going to give some historical context as we examine outdoor air and indoor air contaminants and how they impact human health. And we're going to do a little bit of history on the formation of the Clean Air Act. And then we're going to look at outdoor air versus indoor air quality And then we're going to reference a rather interesting book that's available in the market today by Dr. Joseph Allen and Dr. John McCumber called Healthy Buildings. It's a very compelling read. I invite you to look it up to see how indoor air quality is impacting human health. We're then going to look at ASHRAE Standard 241, which I spoke to a couple of presentations ago, just as an overview, because this standard was written to address the risk of indoor infections within the built environment, and what HVAC practices will be adopted or should be adopted to reduce that risk of infection. Then we're going to look briefly at ASHRAE's position document on carbon dioxide. Yes, ASHRAE has a position document on carbon dioxide, and it gives some context on today's discussion because the impacts of CO2 concentrations inside a building are significantly greater outdoor, and what does that mean for occupants? And then we're going to look at 3 100% outside air system solutions that I'll just speak to. Each of these systems I actually have 1-hour presentations on to educate our market and our industry on how to apply them and include various design considerations for appropriate buildings, etc. So let's move on. Let's examine what the EPA, CDC, and ASHRAE are saying regarding ventilation rates. The Environmental Protection Agency during the COVID-19 pandemic made it very clear that lowering the concentration of indoor air pollutants, indoor contaminants, including viruses, a good solution is to increase ventilation. And by ensuring proper ventilation with outside air, one can reduce the concentration of airborne contaminants, including viruses indoors. The EPA has a clean air in buildings challenge, and of a number of recommendations, Section 2 focuses on optimized fresh air ventilation rates to make sure that acceptable clean outdoor air and enough of it is getting into the environment to create a healthier environment. It goes on to say to increase the volume of clean outdoor air at times of higher risk, which ASHRAE Standard 241 addresses, and then run HVAC systems during all occupied hours, and then think of purge modes during the unoccupied hours to flush out rooms to create healthier indoor environments. The CDC during the pandemic acknowledged the fact that inhalation of active viral or biological agents can actually spread the risk of infection. And a space in their recommendation when indoors is to look at ventilation mitigation strategies, increase the outside air rate. In fact, they go so far as to say, if you can, eliminate HVAC air recirculation. That's a pretty compelling statement. The problem is, or the challenge is, while the CDC, the EPA, and ASHRAE recommended during the pandemic to increase ventilation rates, certainly ASHRAE is advocating for more energy efficient buildings. Their standards 90.1 and 189 and their efforts to promote decarbonization and electrification poses a challenge to the solutions used in reducing the risk of infection in the environment. So increasing ventilation rates beyond code minimum for conventional HVAC systems does reduce the efficiency of that mechanical system, which is contrary to the intent of ASHRAE's decarbonization initiatives. However, 100% outside air systems are an energy efficient system design that provides improved indoor air quality while being more efficient, 25 to 40% more efficient than conventional mixed air medium pressure VAV systems. Energy recovery is used in the 100% outside air handlers serving the spaces, so you actually reduce the load for that building by decreasing the load of the outside air with the exhaust air using heat transfer means that we'll touch on later. There's no return air path in 100% outside air systems back to the air handler. You can make sure that you're getting the appropriate amount of outside air directly into each zone that is measurable and verifiable. And there are multiple types of approaches that we'll examine, at least three, suggest a fourth as well, to consider with these systems. So let's look at what a 100% outside air system is. The design intent behind a 100% outside air system is to handle the outside air or the ventilation air required for a building independently of the mechanical system itself. You do not tap an outside air duct into a mixed air box that mixes the outside air with the return air in a single air handler. You actually have an air handler that is handling all of the outside air independently of the other mechanical footprint. Consequently, if these systems are adopted, they run parallel to the mechanical system, and you can reduce 60 to 70% of the airflow in these systems, resulting in less ductwork and reduced architectural spaces. Being involved in a number of these systems during design and budgeting processes, I want to make you aware that often you hear that 100% outside air chill beam systems or passive radiant cooling and heating systems are more expensive than medium pressure VAV. And you know what? They are. But what is not being addressed is the fact that these systems offer a greater opportunity to reduce the electrical loads, as well as the mechanical footprint, offering energy, financial savings, and the overall architectural features of a building that far exceed whatever differential there might be in running budgetary analysis between a chill beam system against the medium pressure VAV system. So something to consider. So by controlling the outside air with a 100% outside air unit or a dedicated outside air unit, you can now provide the amount of outside air required for each zone in the building. In fact, you can even elect to provide more outside air than code minimum, which begs the question, is it always good to design to code minimum? That really is something, a question that building owners may want to ask themselves for various reasons, hopefully that we're going to explore to some extent today. You can control the CO2 levels more effectively in each zone of the building and provide superior humidity control in these systems. So what is the design goal? The design goal of a 100% outside air system is to use an air handler with a dual tunnel arrangement, one tunnel supplying the outside air or supply air to the building, an adjacent tunnel with an exhaust air stream, and a heat transfer solution that actually bridges the span between the supply air and the exhaust air tunnel. And the thermal energy captured in the exhaust air stream is used to precondition the outside air before that air sees a cooling coil or a heating coil in a building. So let me give you an example. On a 115-degree design day in Phoenix, Arizona, and if you're exhausting 75, 77-degree air, chances are the air temperature hitting the coil in a 100% outside air unit is 90, 92, 95 degrees. So you don't have brute force cooling with these applications, and this is a standard recommended practice. There are two types of heat recovery available. There's sensible heat recovery, where thermal energy is only addressed. And then there are enthalpy wheels, or now enthalpy plate and frame heat exchangers as well, which is a compelling new product hitting our industry recently that actually reduces the thermal energy of the outside air as well as the humidity, the latent energy as well. So these heat recovery solutions are incorporated into a DOAS unit, resulting in the end in reducing the building load by not having to deal with brute force cooling of outside air. So in a decoupled 100% outside air system, the goal is to decouple what is called the sensible load or the heat load or the thermal energy load from the latent load or the humidity load, the amount of moisture in air. You decouple those loads. In a conventional air handler for a medium pressure VAV system, the total load is seen at the cooling coil. In these DOAS systems, however, the sensible load is decoupled as much as possible from the DOAS unit, and the sensible load is handled directly in each space. That's why it's referenced as decoupled. And you drive the sensible load in each space to the heat transfer medium serving that space, a chill beam system or an active or passive radiant cooling and heating system drives the sensible load into the space to a chill water loop. Since chill water is more dense than air, it is more efficient to move sensible energy or thermal energy with a more dense heat transfer medium as water from the space than it is to move the air or move the energy using an all-air solution. And we'll examine why here shortly. So that's where your secondary energy savings occurs, not only in the reduction of the load by using heat recovery in the DOAS, but by also using a more dense heat transfer medium serving each zone within a building. To give you an example why that's important, well, let's look at a conventional HVAC system that uses air as the heat transfer medium for a building. Air is pushed through a building at a high enough rate to capture the thermal gain or the energy gain in that building that results in higher temperatures at thermostats. The problem with air is it will only hold 0.46 BTUs per pound of air. Consequently, air is not very dense, and you need a lot of air to move the buildup of energy within a space, using air as your heat transfer medium. But if you use water as a heat transfer medium, water is more dense than air. In fact, it can hold 8.98 BTUs per pound of water. Consequently, you can move just as much energy with water as opposed to air with a lot less horsepower. The pumping horsepower is less than the fan horsepower that would be required to move the volume of air to provide the adequate heat transfer necessary to maintain building at space set conditions. Well, here's an interesting factor. Refrigerant's even more dense than water. It will hold 88.2 BTUs per pound of refrigerant, which explains why variable refrigerant systems are gaining so much attention on our market, because it provides refrigerant directly to each zone to not only handle sensible loads, but also latent loads. But if you use 100% outside air variable refrigerant system, you can back off on the latent load at your fan coil unit in a variable refrigerant system, downsizing those platforms and consequently making them more efficient. So we'll touch on that later on in today's program. But let's look at outdoor air and indoor air contaminants. And let's look at health impacts of outdoor air versus indoor air. Because you might be asking yourself, well, do I really want to bring in a lot of outside air? Excuse me, my clicker has stopped working. There we go. Do we really want to bring in a lot of outside air in downtown Phoenix on a February morning when we have the visual appearance of a pollution dome residing over the city? Well, if we look at outdoor air pollution, let's examine it, what has happened over the years with outdoor air pollution. There's actually good news. So there's good news, which is always an enjoyment to behold. The Environmental Protection Agency in the report on the environment said that according to the National Emissions Inventory data, estimated annual emissions for 187 air toxics decreased by 58% from 72 million tons per year in the baseline period of 1990 to 1993 to 30 million tons per year in 2024. That's substantial. Examples of air toxics include benzene found in gasoline, perchloroethylene emitted by some dry cleaning facilities, methylene chloride used as a solvent in industries, and the list goes on and on and on. Most air toxins originate, however, from anthropocentric sources. So they're created by humans, okay? So in Exhibit 3 of the Environmental Protection Agency report, it goes to show that emission trends for 7 pollutants believed to be among the pollutants that contribute the greatest cancer and non-cancer risks are for the most part in decline. If you look at acrolein, benzene, 1,3-butadiene, etc., many of them have seen substantial decreases over the early 1990s. There has been an increase in acetaldehyde and formaldehyde, which the report on the environment states is due in part to wildfires and prescribed burns. And we've all witnessed and experienced wildfire smoke in Phoenix, Arizona. If you lived here over the last 5 years, at some summers it's been somewhat of a concern, or a real concern, I would think, for healthcare facilities. And for all of us personally, it should be. The EPA air trends have shown that due to the pollution or the outdoor air pollution standards and requirements, there's been an 81% reduction in carbon monoxide, an 88% reduction in lead, 60% in nitrogen dioxide, et cetera, et cetera. It goes on to say that despite increases in air concentrations of pollutants associated with fires, carbon monoxide, and particle pollution, the national average air quality concentrations remain below the current national standards. So downward pollution trends, what happened? What allowed for outdoor air quality to improve? Well, let's go back in time a little bit. Let's look at the history. There was a tragic event on October 26, 1948, in Donora, Pennsylvania, when a thick cloud of smog composed of carbon monoxide, sulfur dioxide, and metal dust produced by the town's zinc plant and steel mill descended on the town. 20 people were killed and 14,000 people fell sick. The response to that event in 1948 was the Air Pollution Control Act of 1955. Consequent legislation from the 1955 Act, was the Clean Air Act of 1963, the Air Quality Act of 1967, and the Clean Air Act of 1970. Well, in 1970, the Clean Air Act was passed unanimously by the U.S. Senate, and in the House of Representatives, a vote of 374 to 1. Could you imagine a cooperative Congress working like that today? So it was really unanimous in the government's recognition of the need for an outdoor air standard. And Richard Nixon signed it into law on December 31st, 1970. And this is a statement that I found that I would like for you to pay close attention to as we examine indoor air quality. In the Clean Air Act of 1970, it is written, in this law, Congress recognized a right to healthful air quality, a right to healthful air quality. Well, that's interesting, and hold on to that thought. It was at that time that Richard Nixon also established the EPA and assigned the EPA with the task of monitoring outdoor air quality. And the air contaminants monitored in the act are lead, ozone, sulfur dioxide, nitrogen dioxide, carbon monoxide, and various sizes of particulate matter. Has the Clean Air Act been successful? Well, since 1990, fine particulate matter pollution, the deadliest form of air pollution, has declined 41%. I would say that's a reasonable success rate. Ozone has declined by 22%. The National Resources Defense Council report found that the annual benefits of the Clean Air Act programs prevent 370,000 premature deaths in 2020, and they predict it will save 457 deaths by 2030. So that's a 30% death reduction from 2018 to 2005. So pretty compelling evidence. Well, very interesting. What about the indoor environment? What about indoor air quality? What type of standards might be guaranteeing we have a right to a healthful environment? Which indoor air quality standards are written into law to guarantee that? Well, let's look at the EPA statement regarding indoor air quality versus outdoor air. It says that at times, levels of pollutants may be 2 to 5 times and occasionally more than 100 times higher than outdoor air levels. The Environmental Research and Public Health Report stated that according to the World Health Organization, indoor air pollution is responsible for the deaths of 3.8 million people annually. It goes on to say that harmful pollutants inside buildings include carbon monoxide, volatile organic compounds or VOCs, particulate matter, especially small particulate matter of 2.5 and smaller microns, aerosols, biological pollutants, and many others. And the reason for that is becomes very obvious. If you look at the outdoor air pollutant, you have at least the EPA's recommended contaminants that are monitored: carbon monoxide, lead, carbon dioxide, etc. But look at the indoor air contaminant list. You have a lot of off-gassing going on in a building. And the problem is when these contaminants enter into a building, they're enclosed. And it is not very easy for them to escape. So they continue to build up. So, and you have to remember that if your building is getting the ventilation that it's supposed to be getting, that indoor air also includes outdoor air contaminants. Well, what about indoor air quality standards? Well, if you go to the Occupational Health and Safety Administration, or OSHA, they do have a standard, and it was created to bring about legally enforceable limits for exposure to pollutants indoors in 1970 for many chemicals based on a report created in 1968. However, if you go to OSHA's website and you look at the language, which I did when I wrote this actual presentation last year, OSHA's own website states OSHA recognizes that many of its permissible exposure limits are outdated and inadequate for ensuring protection of worker health. So that is the available indoor air standard. A standard that recognizes that at best it's very limited in creating a healthy environment. There's a compelling book out there that has wonderful information, and certainly building owners should look at when they are going to be renovating their buildings or creating new buildings, because there's some very compelling arguments and references to a large number of tests and studies that have been done on this very topic. First of all, the book brings to our attention the importance of the built environment and what impact it plays on greenhouse gas emissions, which in the end impact outdoor air quality. So approximately 80% of the global energy comes from fossil fuel combustion. And as consumers of 40% of that energy, buildings consume 40% of that fossil fuel energy. Buildings influence our health indirectly by contributing to the outdoor air pollutants that exist within our environment. So, with regard to indoor air quality standards, do they exist? Dr. Joe Allen goes on to say that we tend to focus much more on outdoor air quality than indoor air quality. So, is there an indoor air quality standard? And the response is no such thing. And how did we become aware of indoor air quality as being relevant? Back in the 70s, we had what was called the energy crisis. I certainly lived through it, where you had to wait in line for gasoline. In order to reduce the energy burden on our energy resources, what happened in buildings is that the amount of outside air being brought into the buildings was significantly reduced. Buildings were being designed at 5 CFM per person. And it wasn't too long before another phenomenon began to occur called sick building syndrome, whereby a set of symptoms such as headaches, fatigue, eye irritation affected workers in these airtight office buildings believed to be caused by the air pollutants generated from inside that building. Sick building can occur in any type of building, and they are more prevalent in very airtight buildings. Back in the 50s and 60s, airtight buildings were not looked at as a serious objective or goal, because energy was cheap and it gave the opportunity for buildings to breathe, you could say. However, when buildings tightened up, and CFM of outdoor air was limited to such low values, then sick building syndrome was the result. Well, the World Health Organization has redefined what is meant by the term health, and it seems to me to be a very good a new definition. The old definition for health is the absence of disease. The new definition by the World Health Organization is a state of complete physical, mental, and social well-being. So that's pretty compelling. And the World Health Organization is trying to drive throughout the world deeper consideration on improving indoor environments. The World Health Organization goes on to give it so much importance that it says the health of all peoples is fundamental to the attainment of peace and security and is dependent on the fullest cooperation of individuals and states, etc., etc. So why are we ignoring indoor air quality, a place where we spend 90% of our lives, if not more, certainly in North America and Europe? By the time you are 40, one will have spent 36 years indoors. In fact, a third of your lifetime is spent in your own bedroom. So outdoors versus indoors. Again, the United States regulatory system is geared towards outdoor air quality, not indoor air quality. So the Clean Air Act set the national ambient air quality standards that have successfully reduced the outdoor air contaminant levels. The question is an indoor air quality act in our future? Well, let's look at the evidence to see if it might actually occur. Referring back to Dr. Joe Allen and Dr. McCumber's book, Healthy Buildings, and reiterating the fact that we spend 90% of our time indoors, you might think that, well, we're not ingesting as much outside air indoors. Well, if your building is getting the ventilation rate it should, Dr. Joe Allen writes this interesting statistic. Though it's true the concentration of outside air in the building might be less, but since you spend so many more hours indoors, you end up breathing more outdoor air when you're indoors than you do when you're outdoors. In fact, it makes the total outdoor air pollution breathed in 2.4 hours, or total outdoor air pollution breathed in 2.4 hours at 30 micrograms per day, whereas opposed to total outdoor air pollution breathed indoors is 21.6 hours or 131 micrograms per day. So whether you're indoors or outdoors, you're going to be breathing outdoor air, and you're exposed to more outdoor air throughout the hours in a day that you're indoors when you're indoors. The indoor air quality, or the Environmental Research and Public Health Journal has written this, that in an article called The Indoor Air Pollution and Related Human Diseases and Recent Trends, that indoor air pollutants consist of particulate matter, volatile organic compounds, nitrogen dioxide, as I'd mentioned before. But what is gaining more and more attention is the health impact of particulate matter. Particulate matter is defined as carbonaceous particles in association with absorbed organic chemicals and reactive metals. And there are numerous sources for particles in the air in the indoor environment. Well, one of the greatest risks to human health is small particulate matter of sizes of 2.5 microns and less. PM is especially concerning as you breathe it in very easily, and the smaller the contaminant, the more available it is to our bloodstream and our lungs and becomes absorbed into our system. So PM 2.5 micrometers is becoming a greater concern, and there are over 7,000 scientifics on PM 2.5 health effects. I did not have time to read all of them for this presentation. Mortality rates increase by 7% for every 10 micrograms per cubic meter of PM 2.5. Hospital admissions increase, and there's an increase in lung cancer incidence or deaths globally due to PM 2.5. Indoor air quality impacts cardiovascular disease. It increases the rate of cardiovascular disease by increasing the number of blood platelets and creating a risk factor for clotting and increased blood pressure. It impacts our awareness, our personal awareness, our cognitive effects, resulting in impaired health and performance in children and adults. And there are growing studies now, and I've seen a couple of them referenced in Healthy Buildings, that air quality within an office also impacts employee productivity. So indoor air quality can also result in cancer, long-term exposure to certain environments, especially formaldehyde. They're finding out if various buildings tested that even childhood learning centers have unacceptable levels of formaldehyde due to off-gassing from materials used in those buildings. There's also studies regarding the impact of CO2 on occupant health, and there's a compelling article in the ASHRAE journal, I forget, it was in June of 2022, called Revisiting the 1,000 Parts per Million CO2 Limit. And it states that several studies proving substantial evidence of acute exposure to CO2 at levels as low as 1,000 parts per million, impacting significant reduction in cognition and decision-making abilities. Classrooms and schools are showing that there's a direct link between poorly ventilated schools and the performance of students in those schools because of their lack of a power of attention. So there's quite a few studies in this regard. And also other factors impact student performance in schools. One is thermal comfort. A study was done in New York City that showed that a classroom maintained at 75 degrees is 14% greater to have a success in the passing of exams than schools that are kept at 90 degrees. The National Lung Association has a rather surprising bit of data and information on the amount of absenteeism that results from poor indoor air quality in schools, affecting asthma. Asthma is one of the leading causes of school absenteeism, causing an estimated 13.8 million lost school days per year for children between the ages of 5 and 17. So the indoor air quality and the impact on human health is significant. So with all this information available and the numerous studies provided, data is available that demonstrate improving indoor air quality is a good way to boost employee productivity. And the question is and also human health. Will insurance companies realize the savings behind enhancing human health by promoting an indoor air quality standard? It's very possible. And I'll tell you, one of the ways to improve indoor air quality is by bringing 100% outside air systems into our market and into our industry today. I will touch on this standard briefly, just in the interest of time, to make sure we make it through this presentation in a timely manner. ASHRAE Standard 241 has been written now, the fastest standard ever written by ASHRAE, and its sole goal is to reduce the risk of infection within the built environment during times of pandemic or perhaps even aggressive cold and flu seasons. So the purpose of the standard is to establish minimum requirements for control of infectious aerosols to reduce the risk of disease transmission in the occupiable space of buildings. In the foreword of the standard, it says that the catalyst for the development of Standard 241, which was finished in June of 2023, the fastest standard ASHRAE ever produced, was actually due to an engagement with the White House COVID-19 response team that was asking for better standards for indoor air quality so that buildings have the resiliency to go into modes of operation to significantly reduce the risk of infection. So one of the expressed goals of Standard 241 is to make sure that as a minimum, the ventilation rates or outdoor air rates per building as defined by Standards 62.1 and 62.2 are being achieved in a building. It was not uncommon to hear during the pandemic when people, building owners went to check their outdoor air dampers at their air handlers that many of them were closed. So consequently, occupants were just being exposed to return air throughout their building. In the standards requirements section, it states that a minimum of standard 62.1, 62.2 ventilation rates will be achieved, and the standard provides additional requirements, the first of its kind, called an infection risk management mode of operation, which means that the HVAC system has to be able to respond when a building is assigned to be in that mode by providing the adequate amount of clean air that ASHRAE's standard 241 defines as pathogen-free air, not contaminant-free air, pathogen-free air, is available to the breathing zone of all occupants within a space. So the definition of infection risk management mode is the mode of operation in which measures to reduce infectious aerosol exposure is documented exposure in documented building readiness plans, making sure that they're active. And it defines what those building readiness plans are to be. It introduces language on the equivalent clean airflow rate. When a building goes into infection risk management mode, the equivalent clean airflow rate must be attained at the breathing zone of occupants. The equivalent clean airflow rate is defined as the theoretical flow rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on infectious aerosol concentration as the sum of actual outdoor air. Again, outdoor air enters into the discussion. Why is outdoor air considered to be an effective means of providing clean air to the breathing zone? Because it's pathogen-free. There's, if anything, a minimal of agents floating around in the air, of viruses and bacteria. Many of them are destroyed by UV light from the sun. They can't exist outdoors. So outdoor air is considered to be an effective means of providing clean air or equivalent clean airflow rates to the breathing zone. However, the standard is not limited only to outside air. A combination of outdoor airflow rates and properly filtered recirculated air or disinfected air from cleaning air technologies as defined by the standard can also be applied to achieving those clean airflow rates at the breathing zone. It just seems to me that outside air might be a very elegant, simple way of addressing this without having so many components going on in your building or space for cleaning and environments. Anyway, so the minimum equivalent clean airflow rates have to be achieved in the breathing zone as the standard is applied, and it is ASHRAE's intent to incorporate the language of 241 at some time into 62.1. And when it does, it's going to start impacting and influencing codes in municipalities. So be aware of that when it comes by. An example of equivalent clean airflow volumes, if a office building, which is designed to 20 CFM to the breathing zone of occupants, under standard 241, when a building goes into infection risk management mode, that airflow rate needs to be bumped to 30 CFM. And those flow rates vary depending on how those zones are being used within the building, within a building. So the standard lists a chart as to what those values are, and they're freely available. The standard also addresses air cleaning technologies. In section 7, it defines the testing requirements to validate the performance of these air cleaning technologies, such as bipolar ionization or enhanced types of filtration means, etc., or UVC lighting. All of that testing is now, all the testing of those devices and how they are to be done is outlined in the standard. Let's look quickly at ASHRAE's position document on indoor carbon dioxide. As we mentioned earlier, that carbon dioxide too is impacting human health and well-being. Be aware that ASHRAE has a position document on indoor carbon dioxide. It's very interesting, and it's not too long of a read. It has the history of CO2, health and cognitive effects of CO2, existing standards and regulations for indoor CO2, and a number of other topics are covered. And it goes on to state in the position document, as well as in the ASHRAE June 2022 standard, that CO2 can also be used as a way to validate what the contaminant concentrations are within the environment. It's like the canary in the coal mine. By measuring CO2 levels, one can approximate what one's contaminant level makeup is within an environment. Well, that brings a rather interesting discussion. The city of Phoenix, according to a ResearchGate report in 2013, demonstrated that CO2 concentrations in the urban CO2 dome of Phoenix is reached 555 parts per million. In the outskirts of the city, it was 370 parts per million. While ASHRAE standard 62.1 1999 defined that CO2 limits within the building should not exceed 700 parts per million of the outdoor CO2 concentrations, which in the 1980s was approximately 350 to 375. However, if you adopt that logic today to an environment that has 555 parts per million of CO2, you now have a level of 1,255 parts per million. Well, LA is actually seeing 700 to 750. So as you can see, if you use the 1999 62.1 requirement, you're going to be exceeding 1,000 parts per million, which was the 1999 objective. The Robert Stum, well, first of all, the city of Phoenix, according to a Boston University study now in July of 2021, showed that there are now reading 575 parts per million of CO2. And compared to 1990, it goes on to state an increase of 291% of CO2 level increase. The Robert Stum article goes on to say that CO2 levels at 1,000 parts per million induces significant reductions in cognition and decision-making abilities. And consequently, considering the recent studies of CO2 impacting human health, indoor CO2 levels of 1,000 parts per million reappears as a sensible time-honored limit. And there's language of perhaps reducing it to 600 to 800 parts per million. So that is currently being evaluated. Well, one of the ways to control, well, before I go into that, as a national study, the book Healthy Buildings demonstrates that CO2 levels are in far excess of 1,000 parts per million. 95% of the buildings in the nation are registering at approximately 1,500 parts per million. Schools and classrooms are being impacted. In some schools in Texas are reading CO2 levels as high as 3,000 parts per million. The only way that we know today to reduce CO2 there's some new technology out there that we know Daikin now has available for reducing CO2. But the traditional mode is increase your outside air rates because the outside air levels are so much lower than inside the building environment. And the recommended level is now being examined is going from 20 CFM per occupant of ventilation to 40 CFM per occupant of ventilation. I want to save enough time to cover the 100% outside air solutions. Please know that there's a lot of language going on today on how CO2 does impact human health. It impacts our cognitive skills and functions, and is going to become a greater topic in the future, in my opinion. But one of the ways of using CO2 is to make sure that you can use it as a way of verifying the contaminant levels of within a space by tracking your CO2 levels. So the higher the CO2, the chances are the higher your PM 2.5 contaminants are and potentially your VOCs. And the lower your CO2, the lower your contaminant levels. So something to be aware of. ASHRAE's position document on indoor carbon dioxide, however, does offer a word of caution that though outdoor air and CO2 level reduction is something to be achieved, that they are lacking the actual research and testing necessary to bring about, to identify more closely how CO2 is impacting human health and what conditions that it might be resulting in. So 100% outside air systems could be an excellent solution for looking an excellent solution for improving indoor air quality by bringing the amount of outside air necessary that we need to each zone into a building, if not more, in relation to outdoor air contaminants as well, or maybe more, without impacting energy efficiency in a building. So one of the things that's very attractive is that we can actually address indoor air quality more effectively with 100% outside air systems while not paying an energy penalty. I've written, again, a few articles on this, and they are available certainly on Engineered Systems Magazine, but let's look at these solutions one by one. One of them is 100% outside air variable refrigerant systems. We've been using variable refrigerant systems in our markets now for some time, 15, 20 years. Normally what we do, certainly in Phoenix, Arizona, is bring the outside air into the ductwork, serving indoor fan coil units in a variable refrigerant system. And consequently, we distribute the outside air that way. However, it does beg the question, are you actually getting the amount of outside air you need in each individual zone by doing that? How do you verify that? How do you quantify that? Anyway, a 100% outside air variable refrigerant system takes the outside air and runs and provides it independently of the variable refrigerant system, allowing a 100% outside air unit to condition the outside air, bring it to the appropriate space conditions necessary to provide healthy outside air to each zone where it can be quantifiable, and then let the variable refrigerant system run independent of the DOAS. And there are a lot of system advantages for doing that. So these are the advantages for 100% outside air VRV hybrid systems. You bring the outside air directly to each zone under load neutral conditions. By lower entering air temperature at the fan coil unit, because your outdoor air is not mixed with your return air under peak design conditions for both summer or winter. You get improved condenser efficiency on your VRV system because you have lower temperatures at your VRV coils, smaller variable refrigerant system dimensional footprint, less weights, and your system becomes more efficient, and you have better latent humidity control with a DOAS unit that is properly designed with low dew point discharge air to handle the humidity issues within a building. Another 100% outside air solution is an active chill beam system, where instead of refrigerant being piped to each zone locally through an air handler or a fan coil unit to each zone, we actually bring chilled water into each zone in a chilled beam, an active chilled beam. These devices are ducted directly to the 100% outside air unit, and you get enhanced capacity out of an active chilled beam, and it provides 100% outside air directly to each zone. These systems, of course, are more efficient because they use water as the heat transfer medium locally to each zone as opposed to air, and water has so much more heat transfer capability than air because of its density. So consequently, these systems see their energy efficiency by reducing the overall horsepower of a building. It takes a lot less pumping horsepower to move the sensible load than it otherwise would of fan energy required to move the required air. So the total load, again, is decoupled from the air handler of the chill beams. You actually handle the latent load of a building with the 100% outside air unit, and you handle the building's sensible load as much as possible with the chill beams by driving the thermal energy to the chill water loop where it can be more efficiently removed from the space otherwise than air. So it's a decoupled design, and by doing this, your airflow rates can be reduced substantially from 50 to 70% in the space. And I've been involved in a number of projects that have certainly seen that buildings are designed with 0.3 CFM or 0.4 CFM per square foot as opposed to 1 or 1.1 CFM per CFM. So you can get the amount of outside air you want in each zone, whether it be code minimum, if the environment will allow for it, or certainly bump your outside air as required and put the type of resiliency in your DOAS unit so it can adjust and modulate the amount of appropriate outdoor air to bring about the best indoor air quality within the space. Again, these systems are very efficient because they actually reduce the amount of motor horsepower serving these buildings. There are also passive chill beam systems available, another compelling technology that actually runs the 100% outside air parallel to the hydronic component, using displacement ventilation as the supply air delivery of choice. That adds another layer of efficiency, certainly in our Sonoran climate zone, to a decoupled hydronic system. There are passive, 100% outside air, passive radiant cooling and heating systems, and I'm pleased to say ASU has their first building that has used this design concept, or first large building anyway, at the ASU ISTB7 project, where it is decouples again the outside air from the hydronic sensible load side of the system, and it drives the sensible load to the chilled water or hot water served within the radiant panels or sails located in a space. These systems too are designed to low airflows of up to 0.3 up to 0.8 CFM depending on load, and the building humidity again is addressed by the 100% outside air, by drying out the outside air adequately enough to absorb the latent gain in the building throughout its operating life. What's very attractive about passive radiant cooling and heating systems is that they all use all four modes of heat transfer, conduction and evaporation that we see in all mechanical systems, as well as radiation and convection. Radiation at the panels to absorb heat energy generated in the space, or to emit energy in heating mode to the space. And convection because displacement ventilation creates a thermally stratified environment whereby heat sources in the space move the air through thermal plumes. Each of these topics I speak to in various presentations, but this is a very compelling feature of passive radiant cooling and heating, is it allowing the forces of nature, the forces of natural heat transfer to take over without applying mechanical means to do so. Again, by doing that, we actually chill or heat ceilings to cool or heat, and driving those loads to the environment. There are also these passive radiant cooling and heating devices can be radiant panels, or they can be convective sails. Sails offer an element of efficiency of heat transfer because of the convective factor that they offer at the sail. Cold air falls, warm air rises. So the method of choice for passive systems, whether it's passive chill beams or passive radiant cooling and heating systems, is displacement ventilation, where air is brought in at 62 to 68 degrees and not at 55 degrees. We have low discharge out of the diffusers and allow thermal heat sources in the space through the forces of convection move the air and not fan energy. The compelling feature of displacement ventilation is that occupants receive one pass of clean air across the breathing zone, and that warm air captured by the thermal plumes is taken to the upper levels of the room where contaminants are concentrated and the return air and exhaust grills are located, and that air is evacuated not only from the space but from the building with a 100% outside air passive system. And then there's a very compelling approach to HVAC design, 100% outside air underfloor air systems, where we can actually bring outside air directly to each breathing zone. There is no chance of room air being re-entrained in the space due to a return air path. That air is exhausted from the building as any other conventional 100% outside air system would do, but the air crossing the breathing zone is 100% outside air from the floor as a single piston of clean air rising to the upper lungs. So this is today's presentation on 100% outside air systems, the importance of ventilation. They are an excellent solution for achieving indoor air quality, and when properly applied, they offer greater energy efficiency to help ASHRAE and us overcome the challenge of creating healthier environments while using less energy. Thank you very much for your time. Are there any questions?
Thanks, Dan. We do have a question in the chat box. What does this 100% outside air system do for filter maintenance? Does this system increase filter size to a minimum 4 inches?
It can, and it might. And it's certainly, you would just use, we're normally seeing MERV 8, MERV 13. There's no code restriction on that. I think we need a minimum of MERV 8, which is used in conventional systems, but I would recommend MERV 13 to more effectively deal with PM 2.5 particles. You could hear MERV 14, but then again, the more efficient your filtration system becomes, then of course, the greater pressure drop and the greater energy penalty. But I would like our audience to be aware that there is filter technology out there today that can achieve MERV 14 filtration ratings that do not have the pressure drop. And we can certainly supply information on that. And it would be an excellent solution for DOAS units because it offers the effectiveness of treating wildfire smoke, which would be a legitimate concern for 100% outside air system when there is the wildfire aspect. Technologies are out there that will address the smoke issue effectively that would make 100% outside air systems a more viable option.
A comment as well, MERV 13 is required by California Mechanical Code. So
interesting.
Yep.
Okay.
Thanks, Brian, for that note. That is all the questions that we have in the chat. If anybody wants to come off mute and ask a question, if you want to hang out longer, I know we've gone a little over time, so I don't want to keep you guys any longer. We did have a question pop up as soon as I was going to say that. Are underfloor air delivery systems vulnerable to short circuiting of clean supply air to ceiling exhaust due to excessive heat loads, such as uncontrolled solar gain creating hot spots, as is displacement ventilation? Not suggesting this is a barrier, but another reason to control solar gain and other potential heat sources.
Absolutely. And I was involved in a project. In fact, it was the Salt River Fields, I believe, in their main office building that had an east side exposure. And of course, the CEO's main office with a hard floor and the morning sun rising up and heating that floor. And there absolutely was short circuiting of air. You have to be very cautious of that solar impact on the floor that could cause the short circuiting in either underfloor air or displacement ventilation for that matter. So yes, it would be a concern. We have to make sure that that would be addressed either through the type of glazing that's used or the orientation of the room, etc.
All right. Any other questions? All right, as always, if you do have any questions, you can follow up with myself or with Dan or with your Veritech salesperson, and we can help you out. Dan, thank you so much.
Thank all of you. And please, if you think of questions, don't hesitate to reach out. We'll be happy to answer them after the session. And by the way, the presentation will be available on our website if you wanted to review the details more closely. So thank you so much for your time and your interest, and look forward to seeing you next month.
All right. Thank you, everybody. And I will get out an email with the link once everything is uploaded. Have a good rest of your Wednesday.
All right. Take care.
Oh man, my arm.